from where I sit, I see many empirical researchers who are trying to start using machine learning methods in their work. And a lot of people, a lot of cases, the wheel is being a little bit reinvented, and a lot of times the wheel is being a little bit reinvented, maybe a little bit awkwardly. And so I thought maybe it's a good time, a sign that many of us are interested in those methods, and that maybe we can kind of sit back and think about what can be done already. So what I'm going to talk about today is the use of machine learning methods for people who are mostly doing randomized control trials usually. So why I would talk about randomized control trial, obviously it's what I do for a living most of the time. Machine learning and randomized control trials are probably the most important development in empirical methods for empirical researchers in the last few years. RCT, you know what they are, I don't need to talk about. Machine learning is a set of evolving prediction tools, forests, trees, lasso, ridge, neural networks, etc. It keeps moving, they keep having more methods keep developing. They develop in a somewhat haphazard, empirical way. And you might wonder what they have to do with each other, because for the most part, they are after very different things. So if you heard Sandil, for example, talk about why we should do machine learning, he's going to tell you that we should do machine learning because there are a lot of interesting problems that are prediction problems. And machine learning, of course, is mostly suitable to do prediction. And I agree with that. And then for causal parameters, we have, so with the machine learning is trying to predict something with potentially a vast number of variables that can be used to have a good prediction. On the other hand, randomized control trials are not looking for prediction, they are looking for estimating causal effects, and usually they are looking for, the target is a very low dimensional parameters, 1 treatment, 2 treatments, etc. So it seems that they could live in their parallel universe without much having to do with each other, and it would be fine. And in fact, in development, there are many interesting applications of machine learning methods, and some of you in the rooms are working on these methods. For example, you can use them to do poverty targeting at the regional level, at the individual level. You can use it to look at the characteristic of urban landscape, how well a neighborhood is doing, whether it's a poor or rich neighborhood. You can, so for us, for example, it can be, even for people who do RCTs, they can be used as a kind of pre-processing for creating outcomes. And of course, the applications are growing, and it's all great. But what I want to talk about today is not that. It's an area of overlap where you can either use machine learning methods to think about causal parameters, and therefore RCTs become interesting because they are an alternative to arrive at the same solution, at the same problem. So we can use RCTs to validate the extent to which this efforts by machine learning are successful or are not. So that I'm going to talk a bit about that. And then on the other hand, RCT, which we think of them as primarily causal, or aiming as having as target parameter low-dimensional causal parameter, also face problems which are more akin to the big data problems. Usually not because we have a large number of n's, but because we have a relatively large number, or sometimes a very large number of variables, x's, covariates, with respect to the number of observations we have. And there are three classes of problems that can become, in a sense, big data problems. One is what control variables to choose. That's not the most exciting, but it's pretty important because that's a question that we ask ourselves most of the time. Like when you finish an experiment, what should I put in? Should I put any control variables in my regression or not, and how to choose them? The second is that is something which has probably gathered the most interest in the applied researchers until now, is what are the relevant dimensions of heterogeneity in program effects? And of course, if you have any number of, large number of covariates and their interaction, and you want to look at heterogeneity, that, in a sense, is becomes a big data problem where you don't have much structure. So that could become something like a machine learning problem. And the third, and I'm not going to talk about that today, but that's the next project on the pipeline, is we have often situations where we have many outcomes, many potential outcomes that we could look at, and also sometimes many treatments as well. Maybe less so in things that we as development researchers do in the field, but what people do in A/B testing, they start having large number of treatments. So even though they are interested in the causal effect of the treatment, they have large number of treatments. And I assume if they are doing that today, we'll also be doing that in some time. So now we have large number of treatment and potentially large number of outcomes. There are methods that people are already using to deal with that. Family-wise error rate is one of them. But one can probably do much better than that. And, but I'm not going to talk about that today. So what I'm going to talk about today is the first three questions. One is using machine learning for causal effects and what can RCT bring to the table in improving those methods, and then how to choose control variable and how to think about heterogeneity. In a sense, the most important slide was probably the first one, and I'm going to have that again in the last one, which is we did put all of the programs, all of the codes that are used to run this are in GitHub. I think they are usable pretty much without much difficulty. So in a sense, you can fall asleep and think whenever you need any of these things, it's there. So maybe that's the most one reason why this is useful to talk about that today. Okay, let me do this. That's the three things that I want to do today. So first, kind of think about RCT as an opportunity to do a Lalonde type exercises for judging the ability of machine learning methods to give us reliable causal estimates. So I'm going to spend a little bit of time on what is the method that I'm going to subject to the Lalonde test. In part because this is same machinery that is also used to think about the sorted effect, heterogeneity in program effect. So that will be, we haven't wasted our time. So the paper I'm referring to here is a paper by a large number of authors, driven in large part by Viktor Chernouzukov, who is, that's called double machine learning. And the objective of the paper is very much to say, we want to estimate the causal effect of one variable, or two or three, a low dimensional parameter. But we have, there is a lot of heterogeneity between the people who receive this treatment and the people who don't. And what we hope is, and then we have lots and potentially a large number of control variables. What we hope is that if we control sufficiently well for all these control variables, we can estimate the causal parameter. So in a way, that's a very, very old problem. And it's a very, very old answer to the problem, which is, you have some, you want to know the causal effect of, say, education on an outcome. You know that people who get education are different for any number of reasons. It's an age-old method to throw the kitchen sink. It's just a larger kitchen sink, okay? So the idea is if that kitchen sink is really, really, really large and has lots of stuff in it, how do we deal with it? And that's the idea of the double machine learning. Can be used with, prior to that, Victor and Hansen and Belloni had a paper on double lasso, which I'm going to talk a bit more, which is very nice, very easy to use. But this can be used as the concept here can be used with any machine learning tool. So as those become better, then we can apply them. The method starts to be used a lot. So it is kind of relevant to know whether it's any good. but we don't really know much about it yet because it has been validated internally in a way. We're saying that if the condition for it to be true are true, then we recover the truth. That seems to be a minimum requirement, but it has not been validated much in the real world. So that's where I think that people who do RCTs will have opportunity to do that any number of times. And what I'm going to show you today, actually, which is based on work that Michael and Pascaline and I did together, is in a sense not a perfect application, but that's the only one that I have for now. So I think we can do many more. I'll tell you why I think it's not perfect. Okay, so just a few minutes on how we do this. So the inference question is, it's the causal question, is how the predicted value of y change if we increase d by a unit, holding the rest constant. And the only way to think about, the way that you can think about it is run your regression this way. So you regress y on your treatment, and then some potentially very complicated function of the z, and the beta is the question of interest. Of course, if you wanted to estimate average treatment effect instead of this where there is a fixed treatment effect, this can be extended to do that. The trick, which is very simple, is to go back to our Frisch-Vaux idea, which is rewrite this problem as in the partial out form and say, well, you take the residual of regressing y on all the z's, and take the residual of regressing d on all the z's. And the Frisch-Vaux theorem tells us that the beta is just the solution of running an OLS regression of the residualized y on the residualized d. So that was true then, and that is still true today, in the sense that it remains true even if the residualized for y and for d are estimated with any machine learning method. Doesn't really matter. They are as a result of a prediction. So our procedure will mimic this idea. So what we are doing is the only problem with any machine learning problem is the problem of overfitting. So you divide the sample into two parts. And you use one part to estimate your residualized regression, and you use the other part to estimate your OLS regression from the residuals. And that works. So in practice, you do that twice. You cut your sample in two. You run the two machine learning problems, get your residualized prediction, run the regression in the other sample. Then you do it again the other way. That's step 2. And then you take the average of the two. And the theorem is that gives you a consistent estimate of beta, and that there are standard error for that object that can be estimated. One note is that you cannot do this by you say, well, why don't we just run a regression where we put D and then throw the kitchen sink? Why do we need to do it in 2 steps? And so, for example, if you wanted to do it with forest, you would start with a guess, run the random forest with your y minus dd on your guess, and then do the other way, and goes until it converges. You're going to get very good prediction, but you're not going to get the distribution of beta 0 minus beta is not at all centered around 0. So it doesn't work to do it that way, and that's the intuition being that you don't know if you are you overfit on one side, so what is left on D is it could be anything. But when you do it this is just simulating, do it with this method. So you residualize one end, residualize the y, residualize the D, and run the regression on each other. You get something that's centered around the truth. So that's nice. But of course, that's only nice. There's no magic there. It's just the same way that maybe for a while we got super excited about matching, but the matching was only as good as what we were matching on. And in the same way, there is no magic there. The machine learning is only as good as to the extent that all of these variables that you have at your disposal do something to absorb the heterogeneity between the people. And maybe the covariates are not that good. So for matching estimate to kind of us to go back on the planet, to go back on firm ground, the Lalonde paper comparing the results of doing matching and many other things. Actually, I think matching was not even in the Lalonde paper. It was the DHI Weber did the Lalonde exercise for matching. The Lalonde paper did it for other methods, and then DHI and Weber did it for matching. And that has not, now we need to do this for this kind of methods, for this one and other that people are going to come up in the future. So we did it with Pascaline and Michael. We did it for our Ghana secondary school study. I believe Pascaline presented the paper, so I'm not going to spend too much on it. I'm just going to quickly zero in on this particular finding. So quick reminder on that paper, we sampled 2,000 students 10 years ago now, and we have continued to follow them. 600 of those randomly selected got a scholarship. A large number of those that got the scholarship actually went to school. Some of those who didn't get the scholarship also went to secondary school. So what we are going to do is to compare an IV estimate where, so what we are interested in is the effect of going to secondary school on a range of outcomes, your test scores, fertility outcomes, labor market outcome, etc. We are going to estimate in the control group with using this double machine learning methods. We have, like is often the case in many randomized control trials, very rich baseline data sets, probably as rich as it gets. So that's kind of a good test case from this point of view. And then we are going to compare that to estimate the same regression with instrumental variables, where the instrument for going to secondary school is receiving the scholarship. So of course, it's not perfect because you're comparing one estimate with another, and it's an IV estimate. An IV estimate have their issues. And this one has a number of issues. One is that maybe the IV estimate is not a good measure of causal effect of going to school. There could be, for two reasons. First of all, there could be direct impact on getting secondary school on the outcome of interest. There could be a financial effect. For example, people who the inframarginal who would have gone to school anyway, they don't have to pay for it anymore. On the other hand, people who would not have gone to school are losing money. On balance, it sort of evens out, but there could be an income effect for some people going both ways. There could be direct effect of receiving the scholarship. So on self-confidence, on the idea that you might be the chosen one. You could think that you need to work harder because you were so lucky. Any number of things that could give you a direct effect of receiving that scholarship. In addition, a few kids in the control group go to technical institute instead of going to regular secondary school. So there could be also an effect on the quality of the quality of education they receive for the same number of years. So keep these caveats in mind. I'm not going to do much about them, but maybe it sort of undermines the exercise. The other caveat that we can do something about is that, of course, the IV estimate is not the average treatment effect for the population. It's the treatment effect for the local average treatment effect for the compliers. So people who are induced by the scholarship to go to secondary school. So is it fair to compare a local average treatment effect for people who are induced, who might be people who are credit constrained, or people who are particularly smart or perfectly not smart, or who knows what, to an estimate that is going to be the average treatment effect in the population? So this actually can be addressed also by kind of doubling down on the machine learning, which say, well, it's okay, because I'm going to show you in the second part of the talk that we can do heterogeneous effect. So here you can do heterogeneous effect of receiving the scholarship on going to school. It's going to give you a good description of who are the kind of people who are induced by the scholarship, very rich description, as rich as you want it to be. So to give you a very rich description of who is induced by the scholarship to go to school. So we can reweight the machine learning estimate such that on observables at least, and this is a large number of them, the people look similar. The people from whom I'm calculating the population for whom I'm calculating the causal effect with the DML look very similar to the compliers. Okay, so that's so this we can solve. This one we cannot solve, at least not here. So with all that said, what do we find? So this is for standardized test scores. So not entirely surprisingly, you find that the OLS estimate of the effect of education is much larger than the IV. So you tend to have an overestimate of the OLS, which is not surprising because the people who are doing the best in the smartest kids, etc., their parents will want to push them a little more to go to school. So you have the usual sort of ability bias. But this is the test scores after they've left secondary school. So you find that the OLS overstate the IV. The machine learning goes about halfway. And now those two estimates are not significantly different anymore. It's still a little bit higher, but it's kind of certainly became closer. And the weighted one becomes even closer, suggesting that if we have a population that looks the same, maybe we have this is progress. So it seems that there might be enough variables in the data set that we can, as far as test scores are concerned, we can absorb some of the relevant heterogeneity. Mind you, if we didn't have the RCT, we would never have known that. But if one does such exercise many times, which I'm sort of hoping at some point we will be able to do, then we'll learn more about in what conditions this is doing better. For fertility is another one where so there is a large effect of going to secondary school on the number of kids ever had, both in the IV estimate is quite negative. The OLS is is a clear overestimate. And note that when you add the control, that sort of makes sense intuitively, which is what we are doing here and what we did for test scores. It doesn't do much on its own. If we ask the machine to pick the control with that double machine learning estimate, in this case, you get much closer. And in particular, the weighted DML starts to be quite close to the IV. Where we don't make where it doesn't seem to help at all is in all of the labor market outcomes. So this is for 2016. You see, for example, positive earnings. The OLS estimate for any positive earning in 2016 is quite negative, whereas the IV estimate is quite positive. So the selection thing here is which is at play, is likely the fact that if you're rich enough to pay secondary school, you're rich enough to pay tertiary school. So those kids are still finishing college as of 2016. That's why they are less likely to be in having positive earnings than in the labor force. Or maybe it is even related, like they're just waiting for something better, etc. But so we have this quite negative effect in the OLS. And adding control, either the intuitive control or the machine learning control, does nothing about it at all. So this is a place where whatever unobservable differences there are between people, they are not captured by these hundreds of variables that we are attempting to control for. And in 2017, we now have many more kids are working. This is later, they have finished college, etc. So this is gone. But what you're seeing is the opposite, which is in the earning, in the log earning for those who are working, the selected log earning for those who are working, there is an overestimate in the OLS compared to the IV that again is not moving at all, neither with the control for the machine learning, and it's not a complier effect apparently because controlling for it doesn't help. So for some outcomes, this is kind of a note. This is a glass half full, half empty. It doesn't really matter to me in a way what it does. But for some outcome, it seems that we come closer to the IV outcomes. For some, like fertility and test score, quite close. For some, it's very different. As I was saying, I don't think it's perfect because we are comparing an IV and you could not like the IV, in which case you are comparing something which is flawed with something which is flawed, so it's not clear what we should prefer. So I think what I would really like to see is to see applications where we directly compare the RCT treatment effect with or you prefer the machine learning methods. In our case, for example, if anybody in the control group had gotten scholarships, not through us, but through their friends, etc., the ideal exercise to have done would have been to look at the effect of scholarships on all of the outcomes. But unfortunately, too few people in our sample got scholarships irrespective of us. But that's what I think could be done. And then we would make progress on seeing, I think one thing that is kind of interesting as far as a research question is concerned is what kind of heterogeneity you can pick up with observables, what kind of heterogeneity you cannot pick up with observables, and try to relate that to some model of how the selection works, etc. So I didn't do any of that today, but I think this is something that could be interesting to do in the future. So that's that. Choosing control variables, it might be a sort of a little bit boring question for people who do RCTs. After all, why would you choose control variable in the first place? If you read the 80 Invents handbook chapter on RCT, you should just not put control variable at all. You should stratify, don't control. But the world is such place that everybody does control for something or the other. So in practice, I read many papers, and I don't think I've seen very many RCT papers that don't feel like they have to include some control. Especially when it happens that by chance, and it always happens, some variable of the very many that are included in the baseline, someone always goes the one direction or the other. And you worry that, I tend to believe that most applied researchers are very well-intentioned. And so my sense is that people worry that this may bias the result one way or the other. And therefore, they want to make sure that the results survive when we put this control. They also are concerned for precisions, which is if there is differences between these variables. If some control variable happen to be different, they might affect the outcome. So people don't know really what to do. Like you don't feel that you should not have control, and you don't feel that you should control, and you feel bad regardless. And that's something where I sense a sense, I personally have a sense of unsettlement, and I sort of feel that there is this sense of unsettlement is a bit generalized. So I conducted an unscientific survey of applied researcher practices, which is how do you decide what to put in? I never heard anybody tell me the dark scenario that I'm putting it all the variables that will make the stars just align for me. And now that there is no stars in the air anyway, there is no reason to do that. The data suggests that people don't do that, since we don't see we don't see any bunching, any suspicious bunching of T statistics in RCT papers. So what I think people do intuitively, what I think people try to do is that they will include as control variable either the variable which are very imbalanced or the variable that they think would really affect the outcome a lot, or both. And it turns out that doing both is exactly what one should do. If you read the Belloni, Chernozukov, and Hansen Lasso paper, which exactly this idea of you want to regress a Y on a D, which could be a treatment, with a nuisance parameter that you're not interested in. What they're saying is that what you need to do is to include, is to run lasso regressions to pick what are the relevant regressors that predict D, the treatment, what are the relevant regressors that predict Y, and then run an OLS regression, including both set of regressors. So my sense is that this is what a lot of people already do, and it turns out that that's what one should do. So the proposal is that we could just decide to do that, remove the angst, and this is much better than the other possibility, which is to write down a pre-analysis plan that says what you're going to put as control variable, because you don't know at the point where you write your pre-analysis plan what is, how the god of randomization are going to screw you. So this is a way of kind of playing with them to say, I don't know, but I will find out. But of course, you find this out in a disciplined way. So there is no particular reason why you would have any temptation that things would, to pick what you want. I don't think that's what people do, but at least it will make clear that it's not what people do. So what we did is to create a little tool. So the only difficulty of this is that you need to prepare your data set, and then you need to run the regression. So running the double post lasso is now a game, child's play if you have a prepared data set, because there is a very nice Stata command called PDS lasso that implements double post lasso. The only problem is you need to have a data set that is ready. And what ready means is that, of course, they cannot be text, and they cannot be, if you have dummy variables, they need to be horizontalized and that type of stuff. So what we did is that we created a little tool that is also in the GitHub that I was talking at the beginning that helps doing that. Will help clean your data set to make it into a machine-readable data set. You'll still have to make some decisions about what should be there in the first place. For example, when you have qualitative options, how many do you want? Once these decisions are being taken, then you can just run the double post lasso. So basically, you gather your potential control variable. You apply this cleaning procedure to the control for which you can use our tool. You convert categorical variable into indicators, adding the square. You can create interaction if you'd like. That can potentially create a vast number of variables, but it's okay because what lasso is doing basically is to pick the right one, and usually a very small number of variables. Creating dummy variables, dropping the perfectly collinear one, and then standardize everything as 0, 1. Mean 0, standard deviation 1. So we've done that for a couple of data sets, just to see, make the thing run. One hope is that by doing that, you also get a lot more precision, because potentially you now control for everything under the sun. So far, I must say, it has not been for the 2 data sets we've done. It's not been the case. It really does nothing for standard error. That's the bad news. The good news, it does really nothing for estimates either. So the one thing that I was hoping to do, but it's kind of the cleaning process takes time. So I don't know if we'll ever get around to fully do it. Is to do it for a large number of papers, because a lot of papers now have the data available. And then hopefully we would find what we're finding, for example, in this Alcan data set, and you'll find very similar thing in the paper with Michael and Pascaline on the HIV and education paper, that basically the results are essentially the same. So all that to say is maybe we shouldn't control for anything in the first place, or maybe the fact that that's already what a lot of applied researchers are doing intuitively. Means that we are very close to where we needed to be at the end. So I don't think any of that is going to lead to kind of great breakthrough in scientific practices, but it's kind of a useful tool if you were ever asking the question how to choose control variable without messing with your standard error. That's a method you can use. Third thing I want to talk about and maybe spend a little bit more time on is heterogeneity. Because this is something where actually I think we could make, this is something that could actually have substantive applications of interest to many of us. So very often, and again, unscientific survey of papers submitted to various journals suggests that there is almost always in any randomized controlled trial paper, or in fact in any identified causal effect paper, a moment where you want to show how heterogeneous the effects are. Either because you want to explore mechanism, and that sort of helps to know if some people are more affected than others. That's one way to get at mechanism. And the other is because you would want to know, for example, whether, and for policy making, it's particularly important. I'm going to talk about that in more detail later, is whether the effect would be different in a different population. So if the effect, if you have a sufficiently large group of people where the first RCT is being done, it can not only tell you what's the effect in that group of people, but it could tell you what would be the effect be in another region where people are poorer or where people are taller or less educated or more educated. So heterogeneity is very important. And again, we have often many potential covariates that we want to look at. So there is, I think, a clear risk of specification searching. And as much as I don't believe that people do it for putting control variable, it is pretty obvious to me, even by introspection, that you're going to run a lot of regression and you're going to include what is interesting. So that's potentially a problem because we don't know if you've done enough tests and you don't know what was done and not done. It becomes harder to interpret the results that are being presented. Is it just by luck that it happens that it turned out this way, or is it something real? So the solution one, which is sort of maybe the fashion in political science or in psychology, is to pre-register, and maybe come to economics to some extent, is to pre-register and say what you are going to look at in advance. So let me say, if I am the FDA and I'm interested in regulating pharmaceutical firm, I want them to pre-register. Because if the only question you're asking is what the effect of a drug for women versus men, I want to know that it has been, that experiment as it was designed in order to find these questions. I cannot let people, yes, there is a lot of money at stake and there's only a treatment effect. So, but for us, because the objective of running randomized control trial in economics is very rarely to just look at the treatment effect and to say this is the effect of my treatment, because we are not testing drugs, we're trying to learn about the world. The idea of pre-registering all of your subgroup analysis seems to me very unsatisfactory, because you are throwing all of your data because you didn't know in advance, like you just is whatever you were thinking, maybe over 5 minutes or maybe over 5 hours or maybe 5 days. But whatever, when you did this moment, you only had very partial information about what was relevant. So if we only pre-registered experiment, what would, it's kind of very sad. In that case, we should stop collecting covariates, because if we're not going to use them, then what's the point? So still, there is a problem. I don't think pre-registration is a very good solution for us. A potential solution is just to say, to be very upfront, this is, I'm presenting these few things, maybe it doesn't hold up, one should try again. I think that's fine with me, that would be a good way, especially since we put the data out so people can try their own things. This is kind of the point that Gerard and Abhijit and Eric Snowberg did in their paper, which is why let's just present things and be speculative, no problem. And another possibility, complementary to that, is to say, okay, it's like for a control variable, putting machine learning help guiding the process without constraining it. here it's very tempting to think, well, can we use machine learning to guide the process of looking for heterogeneity? So we are not tying our hand, but we are drawing a path in a way that we are going to follow. And you will see a paper this afternoon, I think, or tomorrow, that Natalia will present, I assume, since I saw her and I didn't see the other two. But that use machine learning prediction of heterogeneity, and is asking, is the machine doing as well in predicting heterogeneity of the impact of a grant as the people? I will not tell you the answer, but that's a very super interesting, of course, super interesting use of that method. Another paper that I've seen some time ago, not in development actually, but by Sarah Heller and Davis, looking at predicting who benefits the most from a summer job. Both of these papers use an algorithm that was developed by Meghir and Atkin, which is a minor drawback that it doesn't come with standard error. So then that's what I was saying about reinventing and fixing the wheel, instead of trying to make up some way of doing standard error. Sarah Heller does that by bootstrapping, which seems fine, but may or may not work in this particular case. So here the problem is that, once again, once you've said, oh, it's great, we are going to use machine learning tools to look for heterogeneity, you are in kind of a somewhat awkward position potentially, because machine learning tools are for prediction. They are not for inference. And when you look for heterogeneity, implicitly you're trying to make a causal statement, which is or at least a descriptive statement, which is the effect is greater for the woman. Not to say, I am predicting an amorphous set of characteristics is that this set of people will have a larger treatment effect. You see what I mean? We want to say the treatment effect is greater for women. We don't want to say this set of people will have a greater treatment effect, but I can't tell you much about them. It is just them. And it's the same thing for predictive medicine, which is a use of a treatment effect heterogeneity, where people want to be, if you want to use, personalized medicine, if you want to use heterogeneity in treatment to make a recommendation that's personalized for a person outside of the set of interest, you need a proper inference method. And the tools are not really designed for that, nor are they very good at it. So how to fix that, that's kind of the objective of this paper. So one way to do it, and that's both of Suzanne's paper, one with Vaga, one with Guido, make progress by focusing on one particular method, or defining a narrow set of assumptions under which you can make, we have some theorem to make inference statement with the machine learning tool. And what we are doing, in a way, is a completely different approach. We're going to say, we're going to try and build methods that can be used with any machine learning tool that doesn't rely on much assumption about their validity at all. But we're going to be much less ambitious about what we are trying to get. In particular, we are not going to try and recover the entire heterogeneity in treatment effect, the entire conditional average treatment effect as a function of all the set of Z's that might exist. We are going to focus on key features that might be of interest. So this is going to be much less ambitious, but hopefully these are features that are going to be interesting. Features such that, is there any heterogeneity with respect to this rich set of control variable or not? So that could be a good first question to ask. Because if you don't find any heterogeneity with respect to the rich set of control variable, then maybe the thing that you found between women and men is luck. Second question is, what's the difference? What's the difference between the most affected group and the least affected group? Is there a large difference between their effects? And the third type of questions you might ask is, what are the characteristics of people who are in the most affected group and the least affected group? Say the most affected quintile, or the most affected decile, or the least affected decile. So we are less ambitious in terms of what we are trying to get at. Of course, one can build more objects to estimate them. And then in exchange, we can use a vast all of the tools available and all of the tools that they are going to improve. So let me put some notation and make things a bit clearer. So suppose that you have y1 and y0, your potential outcome for states 1 and 0, and you have a vector of covariate, potentially very large, and an outcome. So y1 and y0 are your potential outcomes. And the first thing you have is the baseline heterogeneity with respect to the z. So we are going to call that B0 of z. And the second one is the conditional treatment effect, which is the difference conditional between potential outcome treated and untreated, conditional on the z. So in principle, that's our target, but we are going to be less ambitious than that. And suppose that your treatment effect is randomly assigned. Maybe there is a propensity score that depends on a subset of the z, and the propensity score is known, P of z. So the observed outcome is this usual formulation. And in particular, it can be written as B0 plus D times S0 of Z, as where S0 of Z is the heterogeneity between the people as a function of Z. And what we observe, of course, is the data, the y1 or y0, depending on treatment status, all the Z and the DI. So we know that the S0 of Z is going to be typically, if you just try to estimate with any machine learning method, an interaction y times equal B of Z plus D times S of Z, what you're going to get is garbage. You're going to get something that is very imprecise, overfitted, and you can't tell much about. Unless you are in specific circumstances, like, for example, you can do it very well with trees, where you say in half of the sample, I'm estimating my trees, and in the other half, I'm looking at the heterogeneity by leaves of the tree. This is the Susan's methods. So what we are doing instead is to say, well, let's cut the sample in two as well. In one sample, we're going to use whatever is your preferred machine learning method to predict baseline heterogeneity as a function of the Z, and to try and estimate S of Z. We know that it's not very well estimated potentially. And what we are going to consider that these maps are frozen. That's the auxiliary sample. It's estimated, however, well or badly. And then we are going back to the main sample, and we are going to we have some results to get the best linear predictor of S0, the true conditional average treatment effect. So the best linear predictor, not the full S0, but the best linear prediction using this SZ that has been estimated whichever way in our auxiliary sample. The average by groups, the average treatment effect by groups, for example, by decile from the least affected to the most affected. And then potentially very interesting for us, in particular when we're thinking about mechanism and things like that, is the average characteristic of people who are in these different groups. And the theorems in the paper is that you can get proper inference for these things. You can get valid inference about all of these features. So we have, for each of them, we have two strategies, but I'm just going to very briefly discuss one of them. So to get the best linear prediction, what you're going to do is you're going to take your S of Z that has been estimated in the auxiliary sample, and then in the main sample, run a linear regression of your outcome on the treatment minus the propensity score, and the treatment minus the propensity score interacted by, with the S of Z that has been estimated in the other sample, and then the expectation of F of Z in your main sample. And the result is that if you run this regression, beta 1 is the average treatment effect, and beta 2 is the best linear projection of the heterogeneity that exists. So why might you want this regression? What's the useful interpretation of beta 2? The really only useful interpretation of beta 2 is that if F of Z happens to be a perfect proxy for the true conditional average treatment effect, for the true heterogeneity, then when you run your regression in your main sample, beta 2 would be 1. On the other hand, if F of Z was pure noise, whatever it is that you estimated is just overfitting, then when you run your regression, you're just going to get 0. So a simple, an interesting, one reason why you might want to run this regression is that it's going to give you a very simple test of whether there is any heterogeneity, any real heterogeneity in the control in the treatment effect with respect to the Z. So before you're going and start on a fishing expedition of where it might be, that's going to tell you whether it's there. It doesn't mean, of course, if you find beta equals 0, it doesn't mean there is no heterogeneity. It might be that there is heterogeneity that you can't characterize by the Z. You might be able to pick it up with a quantile treatment effect regression, for example, but it means that the Z have no power to predict what this heterogeneity happens to be. Similarly, you can cut the sample you can cut your main sample into bins of by S of Z, say 10 bins ranked by S of Z. And instead of running a linear regression, you can run a regression with 10 dummies where you interact D minus P of Z, which orthogonizes the regressor with respect to all of the regressors that are function of Z's, and all of the dummies. This orthogonalization is essential, otherwise you get it's wrong. And finally, another one which I think is very nice is this classification analysis, which is same thing. You have these groups, so you can start looking at the characteristic of people in these groups. So you can look, for example, do I have more women in these groups that are least affected versus more affected? Do I have more educated people or uneducated in these groups that are least affected versus most affected? Now that you are reassured that there is in fact real heterogeneity, that is something that is sensible to do. Yeah.
So how demanding is that in terms of sample size? When predicting that beta equals 0 if you have very large sample error?
Yes. But it's just saying that I have I have not enough information. I don't have enough information to tell. But I'll show you in a few minutes. We did an application where we have 300 observations, and there we cannot do all of these, but some of the ideas can still be used. I'll go back to in a minute. The problem is that you have two issues. One, of course, the more you also need to cut your sample in two. Which doesn't help. So one of the lessons that if one is interested in doing heterogeneity analysis, etc., in randomized controlled trials, I sort of think it's a good idea to think about doubling the sample size, because but the good news is that it doesn't necessarily need to be doubling the clusters, because all of the relevant heterogeneity is at the individual level. So where you get, so sometimes the sample size is more constrained by the number of clusters, and that's not going to be an issue for any heterogeneity that is at the individual levels, because you can split your sample within clusters. To think of that, what I'm doing, which might be even more useful for the rest of us, is to try to convince Victor to think about whether one can do better than splitting the sample in two, whether there is a way of using all of the sample more effectively. And I'll show you some idea. Even here, what we are doing is that we are cutting it in two many, many times. So for inference, if we're getting into estimate the B of Z and the S of Z in one part of the sample, and then running, say, the best linear prediction or the kt in in the other half of the sample. And then we are doing this again. So we are doing this like 100 times, for example. And the estimate that we're getting at the end is the average over all of these replications. And the standard error is also given by what happens in all these replications. So your standard error accurately reflects the process of sample splitting plus the existing heterogeneity, the existing noise that exists in the real world. But one can do even a little bit better, say by not splitting in half, by splitting in less than half. And I think we can improve there because a lot of the machine learning methods, they are not particularly concerned about sample size because that's not really, they can just run the regression another time and they have another 10,000 people and life is good. So part of the reason why it is sort of useful for us applied people to talk to the econometrician is that my experience with my local econometricians anyway is that they are delighted to find problems to work with that are of interest to people like us, which is what, in a sense, started this collaboration with Victor. And so if you have something that you wish to be done, so for example, I wish to have machine learning methods that do not require to split the sample in two. These are problems that can be submitted. I don't know if they can be solved, but they can be submitted. Anyway, but it is correct that I think this sample splitting is the main source of the problem, and it can be worse than you think. It's not necessarily as bad as you think because of the cluster idea. We talked a little bit about the source of the noise. So the source of the noise, there are really two sources for the noise for these various target parameters. One is the regular thing, the estimation of uncertainty regarding the parameter theta conditional on the data split. And the other is that you split. So we develop confidence interval that take both sources into account. And the way that we are doing it is by repeated sample splitting. So one example to show you some how it looks like, we looked at heterogeneity in the Morocco microcredit data that some of you might have seen. So the setup was 160 villages in rural area of Morocco, which were divided into 81 pairs, and then one treatment, one control village per pair were randomly assigned within each pair. In treated villages, the microfinance organization came in, and then the data it started in 2006, and the outcome were measured in 2009. We have now one more wave where we are continuing this work. So we stratified. I was saying you could stratify your sample split by cluster, but certainly if you have a stratified group, you want to stratify by strata to keep member of all the strata in. So how does it work? So you for each iteration, so here we do about 100 iterations. You split the sample into the main and the auxiliary group. You tune and train the machine learning group in one sample and get B and S, the baseline heterogeneity and your kind of rough estimate of the heterogeneity as function of the Z's. And then you run in the main sample the best linear prediction, which is regress on the S of Z, then regress on the treatment minus propensity of being treated, and regress on the interaction of treatment minus propensity of treated. This is a weighted regression where the weights are 1 over P, 1 times 1 minus P. Similarly, you can do the group average treatment effect, and similarly, you can do your classification analysis by looking which characteristics are looked at. So it's not a huge sample, so I think it gives us a good idea of sort of the regular run-of-the-mill RCTs we might have. These are two of the you could try that for any of the machine learning methods you like. You can then even pick the one that performs the best. So this is 2 of them, elastic net and random forest. And you get your average treatment effect and the heterogeneity. Remember that if we can reject 0, it means that there is some heterogeneity. So here we're finding some real heterogeneity. It's not just, we know that there is real heterogeneity in loans, in outputs, in profit, but not in consumption. So that's the first answer, is that, oh, there is actually real heterogeneity that depends on some of the Z's. So now we can look at how, look at treatment effect by most affected and least affected people. So here we've done 5 groups. This is the average treatment effect for the sample. And these are the treatment effect by groups ranked from the least affected to the most affected. And you find that it's only the most affected group that has an effect that is significantly different from the mean from the average treatment effect. And it's the 2 most affected groups that have treatment effect above 0. So this, you've done that for loans. You can do it similarly for outputs and for profits. For consumption, we had not much heterogeneity in the linear, and you can see that it's also the case that all of these look like they overlap a lot. And finally, now that you have your most affected and least affected group, you can try and say something about, so these are the same. You can try and say something about the characteristic of the people in this group, what is different about them, simply by regressing the characteristic that predicts that you are in this least affected group versus the most affected group. And here what comes out is that it's the younger people who are more likely to borrow and also have higher profits. And perhaps not surprisingly, it's the people who already had some sort of non-agricultural employment that are more likely to borrow, and the people who didn't have loans, although that's not that the difference here is not significant. So these are the 2 things that are coming out as predicting the heterogeneity. In this case, there is probably nothing to write home about, but we notice that there is heterogeneity. And I guess it's the younger people who are more into taking this up. Yeah.
So the characteristics don't have to be the same.
No, they don't have to come up to be the same. Just happens. It's also the case that we don't have an enormous amount to the baseline was done not an enormous amount of characteristics. So these are, in this particular case, the list of characteristics per se is not enormous. But no, they don't have to be the same. It's whatever, and here we've put the 3 same systematically on the graph, even when they didn't come up anyways. So that's for microfinance. So now I want to spend the last 20 minutes, if you bear with me, talking about something that's not even development. But it's an application that is perhaps more substantive than. So I think what Natalia is going to talk about later today is kind of an interesting substantive application of heterogeneity. Here I just wanted to demonstrate that it can be done, and there is some heterogeneity. In microcredit, where we are taking it that might become interesting is that in the long run, what we are seeing is that once we know that there is heterogeneity in the take-up of the loan, then you have a set of people that you can predict is absolutely unlikely to take loans. Very, very unlikely to take loans based on the observables. So then you can look at that group, since there was once microcredit was available, it was available for everyone. So you don't have anybody who is excluded. But if you have a group that's based on observable, we can say has never taken loan ever, then they can be used to look at external effects on other people, market level effects, etc., which of course in microcredit organizations are interesting. So we can know whether this is for them a positive thing, that there is microfinance or not for people who don't borrow. So that's where we are taking that's where it might also become substantively interesting in this case. The last thing that I want to talk about is this application, which is from France, which is not a developing country, which is doing very well, but is particularly well these days. But is something that is a question which I think is comes up very often, at least in JPAL, for example, it comes up very often, is you're interested in comparing two interventions. And when you're interested in comparing two interventions that have the same objective, of course, the best situation is when you have run two treatments in the same population at the same time. So then you're definitely in a very good situation. But it is often the case that we want to compare across papers. So you want to compare the effect of textbooks to the effect of remedial education. And textbooks were done in Kenya, and remedial education was done in India. So there are differences across the programs, and there are also differences across the population. And it's, of course, it's an active literature to explore how the results change when you have similar intervention in different contexts, or different intervention in the same context. And then sometimes you're in this position where you have different intervention in different contexts. So here we were in one of these situations. And basically our objective is to know, well, we have a slightly different population. Can we predict what would have been the effect of intervention A on the sample that end up getting intervention B, so that we can compare apple to apple in the most fair way possible? So that's, of course, another way in which this heterogeneity analysis might come extremely handy. So I'm going to walk you to the steps in this case of the French program, but this is something which, again, might be, I think, very interesting as more and more of our data is, not only you run regression, but the data becomes available, then people can get it, put it together, and start estimating a sort of 21st century Hoake-Blinder tab decomposition of this is how the effect, this is the reason why the effect varied. In part, it's because of the makeup of the population. In part, it's because of the treatment effect being different. So that's sort of one way in which this could be developed that would be very interesting. So here we try to do it, but with a relatively small sample and not as much data as we want. So to some extent, we had to kludge it a little bit. So I'll do it step by step and explain how we did it. So we are comparing two programs. One is launched by a microcredit agency called ADI, and it was called Création. And the other was launched by the social service, and it's called Groupement Créateur. And both interventions target young people who are out of school and out of work, usually in difficult neighborhoods, either suburbs of Paris or pretty distressed places throughout France and also in French territories overseas. And they target some of these youth who are not in a good labor market position, usually have a bad, checkered school history, etc. But they have a self-employment project. So, for example, they want to build a beauty parlor or they want to build a gym. They have this idea that they can have a self-employment project. So both of these programs, Création and Groupement Créateur, target these kids. And their objective, of course, is to put them back working. But there are some differences, two important differences. One is the ADI program is selective in the sense that out of these young people, they will try and take the most enthusiastic and the one who they act more or less together. So they actually have a real project. For example, they want to start a beauty parlor, not something that makes no sense, that I don't have I'm trying to think of something and then I think, well, actually it could make sense. Not something that makes no sense. So they have some idea. So for example, a pharmacy. I met a girl who had not finished high school and who wanted to start a pharmacy. So it was not gonna happen. So in the ADI program, she would have been kicked out of the program because she doesn't have a live project. And in the groupement creator program, she would be taken. So that's the first difference. And the second difference is that, and related in a way, is that ADI really emphasizes the self-employment project. And what they're trying to do is to give them the technical skills to succeed. So you want to start your beauty parlor, this is how you do a business plan, this is where you get a loan, this is how you get your auto-entrepreneur registration complete, et cetera, et cetera. And they use retired small businessmen to help them. The groupement creator starts from the project and then uses that as a part of a conversation to try and see what makes sense for that kid, which could be self-employment or, in fact, often could be to just get a job. So that's kind of the difference between the programs, okay? So we estimated, so the evaluations were done almost concurrently. And what we found is that the effect of the ADI program across outcome, the ADI program just has no effect. The val test for all of these key measures is 0. It really has no effect. Whereas the groupement creator program tend to have very positive effect. For employment, is not quite significant, but for long-term employment, employed for a wage, it's actually quite significant. I'll come back to that. They earn more wages, and they get less welfare payment. And so overall, the groupement creator program seems to be effective. Interestingly, the effect, they are significantly less likely to be self-employed than in the control group. So you can see how they start from the self-employment project and then they gently prod them towards something that's more sensible. So when we got this, like the first paper I wanted to write was that clearly these groupement creator people get it right. They start from the project and then they move to what makes sense. They don't push people into self-employment, the paper I wanted to write. And then we realized that this was not going to be, you couldn't quite write that paper because the ADI and groupement creator populations look different. So I haven't put all the tables of the paper in the presentation, but the first thing in which they look different, observably they are different. The ADI kids are a little bit older. They are a little bit more likely to have already a self-employment experience. They are more likely to come from mainland France and less likely to come from the overseas territory, etc. So the first thing that I thought we could do is let's match by this observable characteristic. So we match by the observable characteristic, and it doesn't make much difference. The groupement creator program estimated on the observable, these few observable characteristics that we have in common still looks significant, and the ADI program, if you estimate it on the GC observable population, still looks insignificant. Okay. But then we realized that even after you do that, the populations still don't look very similar. And how do we know that? Is that because we can look at the control groups of both populations. And what happens when you do that is that you realize that even after you fully match for these few observables that we have in common, the control group in ADI is just much more likely to have found some job anyways. So 68% of them become employed after about 2 years, which is when we have our end lines, and 44% of the groupement creator program become employed. So the truth is that you find also, of course, in all sorts of social programs in the US as well, is that kids get employed anyways. And here, they are more likely to get employed in ADI program. So, and this was true even after controlling for this difference in employment rate was true even after controlling for these few observable characteristics. And here, where we have a problem is that the ADI program selects on the basis of an interview that we don't observe who they want to keep. So presumably they select people who they think are going to do well in their program, which probably correlates very strongly with doing well anyways. So they pick those guys. And unfortunately, we don't have very rich baseline variable for the ADI program. So not only we don't know on what basis they select, but we don't even have a way to reproduce it. What we do have is we have very, 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 very detailed characteristics of the people who participated in the groupement creator program. So for them, we have tons of psychological variables, how they feel, their views on life, their optimism, etc., etc. We have lots of those. So we have lots of those for the groupement creator program. And of course, because the groupement creator program does not select, we have we can see how whether the kids some kids are doing better than others in this program. So the question we want to ask then, that we can ask, we cannot ask the opposite question, we can ask what would have been the effect of ADI if they took everyone, because they didn't take everyone in the first place. But what we can look at is what would the effect of the groupement creator program be if they had only picked people who looked like they would be like the ADI selected guys. So how do we do that? We try to predict in the control group the probability of finding a job anywhere based on the baseline characteristics. So we estimate the probability to be employed without treatment in the control group. We look at whether there is heterogeneity in treatment effect according to this probability of being employed. And then we are going to try and estimate so I'm going to show you that in fact, there is heterogeneity in the effect of the program according to your predicted probability of being employed anyways. And then we estimate the groupement creator program in a population that is made to look like, observably, similar to the ADI population. And how do I do that? I pick them, I sample them to have an predicted employment probability similar to what our control group people have in the ADI program. So that's kind of the game plan of this paper. So the way that you do it, so the first thing we need to do is this first step, estimating the heterogeneous component, which is estimating the probability of being re-employed. We suffer here because we have 300 observations. So first of all, we can't do the very complex machine learning method. Forget it. It's like we have, of course, more covariate than observations since we have so few observations in the first place. So what we do is that we do cross-folding, which is like this many times partitioning and taking the average of the two to try and use our data set the most effectively while avoiding the overfitting. And we estimate a lasso because that's something that is not too demanding. So we estimate that's something that can be done on a reasonable sample size. So we estimate, every time we randomly partition the sample in 10 splits. For a given split, select our predictors, run the logit model, do that 300 times, and then for each observation, so each person, we take the median of the 300 prediction produced for this observation. That gives you your predicted probability to be employed if you don't have the program in the treatment and in the control. Then we estimate a specification very similar to the one I showed you before with the S of Z's. But since instead of using something completely unstructured, I'm using this predicted employment probability. And following the lessons as before, I am orthogonalizing properly to avoid getting bias, and I'm using a weighted regression weighted by 1 over PZ times 1 minus PZ. And as before in the previous paper, rejecting the hypothesis means that there is no relevant heterogeneity according to predicted employment probability. So you see, it's like here in this case, I cannot afford to try all of the heterogeneity in the world. I'm going to put some structure, but the structure is still kind of flexible. I'm trying to make all fit in via this predicted employment probability. I'm passing a bit on the detail, but believe me that I think that we did things properly enough that there is not a chance of over-predicting the probability of employment in the control, which would of course be unfair. that if we pick people who are very likely to get employed, then of course they are more likely to be employed. So I think we did that properly. So the bottom line is in this first row here, is that the probability to be employed, the effect of the GC program on average on the probability to be employed is 0.18. But the effect becomes smaller and smaller for people who are much less likely to be employed in the first place. So this is what Heckman calls cream skimming, although I think he had in mind more that the cream skimming would go the other way, which is the people that are cream skimmed would be the ones who would be more likely to benefit from the program. And of course, it's going to depend from program to program. In some cases, the selection is going to be it's going to pick people who would benefit the most from the program. In some cases, like here, it picks people who would have gotten the job anyway. They are, enterprising. They have a project. There is many other people who would give them a job or a loan. So intuitively, it might be that it explains to some extent the difference in the result. One way to see it graphically is to look at imagine different groups which select differently their people, and so they apply different thresholds to let their people come in. So each orange dot shows the treatment effect if you pick the 20 best, for example, in this one, the 20% best kid according to their probability to be employed. So you see that you get no treatment effect on employment. And if you pick the 20% worse kid, least likely to be employed, that's where you have the largest treatment effect. So that's the equivalent of the group by group that I was talking before. So the difference between, the effect of the groupement creator happens to be largest for people who have quite low probability of employment anyway. So at least this program, of course we don't know for ADIP per se because we haven't done it, but at least this program was particularly effective for people who, in the absence of it, would have done extremely poorly. Okay, so in itself it's interesting. And yeah. Yeah, so we also have wage. And so the heterogeneity was all done for employment. So we also have done labor income, wages. All the heterogeneity is based on employment. So you can see that it's all negative. And if you put them all together jointly, they want to be negative. But the wage itself, the effect is really noisy. It's a chance to be employed. So your effect on your probability of employment at end line.
Yeah, but you start from much lower, so it's much more room. I mean, that's what you were saying.
Yeah. So no, that is true. Yeah, it is true. But it's not necessarily mechanical because even in the AD control group, it's only 60% of the kids who are employed at the end, and the treatment effect for nobody is 40%. So we don't reach 100%, but yes, in part it's mechanical. Although the AD people would say, no, but there is no point. No.
Mine was better than mine.
Yes, and it's because I put myself 125. So soon your 5-minute thing is. So the AD people would tell you, but there is no point working with people who don't have their act together whatsoever. So one could imagine it going the other way. Yeah. So last, and this is actually my last graph and last slide, is that then the last exercise we do is to say, well, now let's pick weights to create in the GC population, a GC population that looks observably like the AD population in terms of their predicted probability of employment. So the first thing we did is this, which is sort of a naive way to do it, which is this is a true distribution of probability of employment in GC, and these are the weights. The first thing we did is we said, let's pick people, the best people in the GC group, best as in most likely to get a job anywhere, until we find on average the same predicted probability of employment than the AD control group. And this is going to be our similar population. That's the first thing we did. And then we realized that it's a little bit naive because then you kind of throw away all this data, but it could be that some of them would have been picked. And then it turns out that there is a whole literature in sampling to create a population that basically sample from a population, a subpopulation, constrained by whatever it is that you're interested to constrain. So having discovered this literature, we did something that we picked. So there are various ways to do that. They have different ideas. But one possibility is the paper by Heinmüller, is the idea that you pick people, you pick weights such that on average, you have this constraint that on average, the predicted possibility of employment is going to be what you want. So in this case, it's 68%. And so people who are more likely to be employed are more likely to be picked, but everybody has some chance to be picked. These are actually our weights, and it follows a logic, basically. So it represents the population and satisfies the minimization criteria on noise. So we did that to look at to what extent are the difference between the program explained by that. So there, unfortunately, is where we are hit a little bit by our very, very poor sample size, which is basically the result of all of this effort at the end for this last graph is a little bit of a bunch of noise, which is, it could explain, but it's too noisy to tell, which is you have this is for employed, the effect for groupement creator. The effect for AD is actually a negative point estimate. And then the effect for the Heinmüller weight is 0. So it's not negative anymore, but all of these have very large standard error. And for wage employment, we have a significant effect of groupement creator, negative effect of AD, but insignificant, you saw that. And here the weights are doing almost nothing. So here, at the end of the day, I think we are pushing the data a little bit, our 394 observation a little bit further than they would like to go. But I still showed the table because that kind of finalized goes till the end of this particular journey. I do think that the process and the steps, until this very last table, we had the results that were sensible, and the steps could be useful in other similar applications. So I'll put that back again. The most important slide of this talk is here. I hope you find something useful, your student found something useful. We are very, very happy if this is being used and abused and misused and everything. Thank you very much.